Yes? Do we start? Okay, well, first of all, I'm not going to get into this, but I'm told by Aditya that nobody got the last problem of the quiz, maybe? And, I mean, I'll give full credit if you pointed this out. I mean, remember the conditional expectation given any random variable is a function of that random variable, you know? And so the first thing to recognize is what you were given that y takes only two values, you know? Y was either 1 or 0, depending whether omega is in B or not. And you take any function of y, it's going to take on two values, you know? If y is 0, then you get g of 0, and if y is 1, you get g of 1. So you can, you know that this conditional expectation takes on two values. You can kind of guess what the answer is, you know? It's going to be conditional probability, and you can verify that. I didn't expect you to do all that, you know, but anyway, the thing is that you have to know this, okay? You gotta, when I talk about speaking the same language, you have to know conditional expectation means you're getting an optimal estimator of this random variable in L2. You know, and my God, I mean, you know, we're advertising this as sort of being like a machine learning course. What could be a more fundamental machine learning question of coming up with a function of the observations to predict, you know, some other, you know, other thing. So this couldn't be more important. All right, so make sure you understand it. So we're closing up on limit theory, and we have these limit theorems so far. And excuse the green, I realize it's not very visible, but we have the law of large numbers, which means if you take a sequence of ID random variables, it's convenient to introduce a function as well. And you look at the average of the function of those random variables, it converges to the mean almost surely, provided the mean exists, okay? Which means that this isn't like infinity minus infinity. So, you know, you need to know what it means for the mean to exist. We didn't prove this, it is very deep. So the proof that convergence in probability holds is easy. But almost sure is really, you know, it takes some muscle way beyond the scope of this course. So there's no way, wouldn't touch it. CLT, I claim, is a triviality. Once you have this, so this is hard. Oh no. This is easy. All right, so you basically look at the characteristic function of this baby, and you do a simple Taylor series expansion, and you find out that the limit of this is the characteristic function of a Gaussian random variable, and we know if characteristic functions converge, we get convergence in distribution. So you need this fairly deep lemma. It's not very deep, you know, but this CLT is like, you know, a very, very simple result compared to the LLM. Then we get to Cramer's, which we've been applying. So I applied it. I showed how you could derive Shannon's capacity formula in communication theory. You can get all this insight in the geometry of hypothesis testing. But we haven't proved this yet, and today we're going to do it. And the only reason I'm doing it is introduce techniques that are really, really valuable in other contexts. You know, like I'm not proving this because the techniques are way out there in math land, and I don't know if they'd be useful to you in the future. This I know will be if you're going to stay in like machine learning, systems area, you know, communications control, signal processing. This will come up. This is the proof of this result. Again, not in the context of large deviations, just it's a trick that's beautiful, which I'll explain. Yep. Yeah.
Question.
Yeah.
So in Cramer's,
Yeah.
whatever is in the parentheses,
Yeah.
you talk about it, how it's like integral of f and p and dx, and it's like a dot product in a higher dimensional space.
Well, no, I mean, I was just lazy. I mean, the thing is that I don't want to have to, you know, we have this 1 over n, sum k equals 1 to n of f of x k, and count the number of symbols, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 symbols. And that turns out to be the same as this. You know, it's a sum because the empirical distribution takes on at most, its mass is on it at most n points. So it's a sum over the support of this guy. I've reduced the number of symbols, I think. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So I reduced the number of symbols by a bit. But it still takes a long time to keep writing stuff like that down. So I just wrote, you know, f dot pi n. I mean, look, that's a dot product of two vectors. That's all. It's nothing to do with like Hilbert spaces. I got emails about, are we looking at Hilbert spaces in some, blah, blah, blah. I know a dot product of two vectors. Right? I've got, yeah. Yeah, it was just, look, now I've got 1, 2, 3, 4, 5, 6. So I'm just saving ink, and my carpal tunnel syndrome. That's all. Yeah.
Because that's what helps us talk about the half space.
And yeah, that's also, it does, the fact that this is, it helps to emphasize that this is a linear operation, for sure. If you fix f, it's linear in pi, and if you fix pi n, it's linear in f. That is helpful. I mean, it's true. It's not just to save space. But it's five-dimensional, linear algebra. It's nothing deep. And so, on Tuesday, Aditya, so I was in New Orleans until a few hours ago. Aditya begged to present stochastic approximation and just give you an overview of what it means. And it's a generalization of the law of large numbers. So this is like, think of that as like an algorithm to estimate some desired parameter. This would be theta star. But it comes up a lot that you have problems like this where you want, here the goal was to find a root of this equation. It's fundamental in reinforcement learning, for example. It comes up in all sorts of different areas. And I don't know if Aditya, if you explained this, but this is a generalization of this. Did you get into, is that how you motivated it? I don't remember. Yeah, okay, yep.
You said that's a generalization of that, but then
this is, I can.
I've got a question. Is that bottom, so the essay, is that a generalization of the least mean squares?
No. I mean, it's just not, it's not.
It looks sort of similar.
Yeah, I don't know if LMS, I mean, maybe LMS is an example of stochastic approximation. I'd have to go back and review. It's possible it is. I'd have to go. But this is it's just what it is. You want to solve an equation like this, and very often this thing works.
What would be like your gradient term? What would be the G over?
Well, that's an example. So in the context of optimization, this might be a gradient of something, absolutely. Yeah. G might be a gradient of another function you're trying to minimize. Yeah. That's very true. So sometimes you're trying to minimize over theta of an expectation. Sorry. So I'm just writing x, because xn, it's IID, the distribution, so it depends on time. And very often you can take the gradient inside the expectation, Well, like this. Yeah, so here it is. So very often, so if you want to minimize a function, assuming this is continuously differentiable, you look for stationary points where the gradient is equal to 0. All right? And very, very generally you can you can exchange the gradient expectation. Not always, but very often. And then you get, when you do that, you get that G is just the gradient of J. And that's a very common example of this application. I mean, so at NIPS, which is the big machine learning conference, half of the papers almost, a third of the papers are about that. Coming up with fancy algorithms to make that more efficient. Their goal is that. And they have algorithms like that. It's just, it's amazing, absolutely amazing. That's still such a hot research topic, is making this more efficient. If you just apply this, it won't work. You really have to know how to do it. I mean, you need to have the right, one won't work, maybe -1, maybe -10, maybe you need a matrix gain. I mean, and it just doesn't work unless you know what you're doing. Yeah. And a lot of it has to do with the variance, which was talked about. And it's the same, and that's related to the variance that appears here. Yeah. Okay, because this variance here is related to the rate of convergence in the center limit theorem, if you think about it enough. Good. Okay, so So let's go through and play with this. So we're going to go prove this. Now remember, we already have a bound in one direction. So we actually have a fixed n bound for every n, which we've proved already. So I'm slipping in some notation again. I don't want to have to keep writing this sum out, and I can't always talk about empirical distribution, so I'll call that the Sn. Okay, and when I presented all this, I didn't have an F, so we introduced an F because there's a lot of reasons. I mean, the geometry makes it pretty. It's really clear why we'd care about the F. So we proved this. Remember how we proved it? You know, we basically took this, we put the n on the other side, we took the exponential, multiplied both sides by a parameter theta, took the exponential both sides, applied Markov's inequality. It's like 5 steps, but very, very simple steps. And we got this bound for each n. All right. Now that's the nice thing about IID, by the way. If this was anything else, then that would not be, we wouldn't get such a nice uniform bound for each n. So we're really exploiting the fact that they're independent. All right, so it's much, much harder if things aren't independent. But anyway, given that, you know, if I take the log of both sides and divide by n, I mean, I'll write it down. All right, so I take the log of both sides. The log's a monotone function. I can do that. I divide both sides by n to kill off the n that's in the exponent. I get this inequality for every n. So in order to prove a limit, the fact that it's equal, we need to get a lower bound. Unfortunately, we can't do it like this. Getting a lower bound, which is uniform in n, it's called the Bahadur-Rao theorem. I'm not even going to spell it for you. But there's a uniform bound, and it involves all sorts of extra terms. And so we can't get a finite bound. All we can do is get a lower bound of the limit. And that's what we're going to do in the next 20 minutes. All right? All right. So remember all this pretty geometry here. So basically this over here was the set of all probability measures whose integral with respect to f is greater than a. And you notice I'm writing an integral here. I just feel silly writing sums. I mean, it's just absurd. You don't need anything. I mean, I don't need these guys to be evolving on the real line. They could be anything. I've got a function, I've got an ID sequence, and it really doesn't matter. I restricted to x living on a finite alphabet because it was easy in the beginning. Today, it just seems ridiculous to assume that, okay? So I've got this half space here. I've got this relative entropy ball. What was that again? So QD of P So this ball here was the set of all probability measures whose relative entropy sort of distance to p is less than d. And in this case, we're gonna firm this up and identify what all these things are, what Q is and what D is and all that business. And so a lot of it's sort of a review. Let's recall from last week what all these things are, besides the definitions. Oh yeah, well, one more definition. I mean, let's see. No, yeah, so this Q here is going to be special. So recall that we had this definition. So this constant here that doesn't depend on x, it's defined so that this thing integrates out to 1, all right? Now I know the notation looks strange. This is just symbolic, it's code. What I really mean by this is that if I take an expectation of some function, say, I mean, f's been taken, but it's okay, f of y, that's equal to the expectation of e to the L theta of x, f of x, and somebody tell me what I mean by this. What is y and what is x? And any f. So just look at this strange thing here. What do I mean by p of dx? It doesn't mean anything. It's just notation. This is shorthand for what I really mean is this. For say whenever both sides make sense, whenever the expectation makes sense. Say whenever f is bounded. I don't need bounded, but let's throw that in. So whenever f is measurable and bounded, I have this. What's y and what is x? I'll make sure you're with me. Given I'm trying to explain this code, this notation. Yep. Yeah. All right. So that's just notation for meeting this. And so L theta is the log-likelihood ratio between the two guys, and it can be defined in completely abstract settings, and you just mean this. Okay, x could be living in some weird space, not just the real line, and you could still define a log-likelihood ratio. So L theta is the log-likelihood ratio, and e to the L is the likelihood ratio. And you often use a lowercase for that. And another notation is you write that as dq dp. Again, that's just notation you'll see all the time for likelihood ratio. It's sort of a derivative. All right, cool. Even though it's ridiculous, it's not dp dq. It's nothing to do with calculus notation. It's awful notation. This is much more reasonable to say that q of dx over p of dx is this likelihood ratio. All right. Horrible. I mean, notation is awful. I apologize. It's not my fault. But so what is q? Q, we actually worked on this before. So I was building up to all of this. I'm going to explain to you why Q, the Q that we care about here, and especially I've got an F right there. F is the same F that appears there. It's the same F that appears here. Q is one of those Q thetas. Let's put a star here.
The other way around.
Okay, so anyone could have guessed this, okay? I mean, just looking at this picture, I've defined this half space of the set of all probability measures such that when you integrate f with respect to mu, it's greater or equal to a. I'm here on the boundary of this. That boundary better be the set of probability measures for which the integral is equal to a, all right? So I've written this as it's actually on this ball from here and here. The fact that it's on this point here, it's also on the boundary of this entropy ball. The relative entropy between Q star and P must be D, you know. But we already saw that, I mean, we saw that playing around earlier, that's actually is I. It's the same as the I of A we did there. I said all that. I haven't really justified it very well. I'll justify it perfectly now, all right? Because we're going to basically, I mean, you know, I've been saying this, and you must have thought I proved it, but I've just been taking it for granted. All this geometry, some of it, some of it I made precise. The fact that this half space is on one side and the ball is on the other, we nailed that last week. You know, but a lot of other things maybe aren't completely clear. So let's put it all together. So there's a lemma that we've really proved last time. It's lemma 4 in these notes. And it's also in Hayek's notes. So I wish I could keep writing that, but it'll scare you off too much. I guess I'll avoid it. But this is not quite a dot product, but you still use that notation. But this is what we called A of theta in previous lecture, like last Tuesday, a week ago. We just gave it a name. So when we performed this derivative, we called it A theta. All right? And as it turns out that the relative entropy between Q theta and P is equal to I of theta for all theta. All right, so that comes about from the definition of just from what you know about log moment generating functions, and we did prove this before. Maybe I'll do it again if you want me to. I don't know if we should, though. So if you look at your notes last week, we proved this. It's a very, very easy thing to prove. Just like the moment generating function, the fact that it generates moments, that's what we're saying here. See, we're generating a moment by taking a derivative. That's what moment generating functions do, and that's what the log moment generating function does as well. Okay. Things get a little trickier when you take the second derivative. So because of the log, when you take the second derivative, you get the variance, not the second moment. So, and then we have this geometry, which is sitting right there. And so you notice we've been taking theta positive throughout. So so basically the last result is just repeating the geometry we've talked about already. All right, so we've done this already. I just want to repeat it again and just, I really encourage you to go and, it's all been wrapped up together and summarized in Lemma 4. We did this in bits and pieces already. I don't think I should repeat it, but it's really useful to go through and review it again on your own. And now what I want to do is I want to use this result, again, I mean, to prove this, you just go through and look at the definition. Again, I'm not going to do it. But we're going to use this result now to go and prove Cramer's theorem. And I keep bragging about this one little special point that's important, and all of it's involved in looking at x and y, basically. So reality is that the random variables come from x. We're going to pretend they come from y. And by doing that, by pretending that the observations come from q star instead of p, we get Cramer's theorem in the remaining 10 minutes, or whatever it is. All right. Yeah. Yes.
So that f should that be L or should that be for any f?
Wait.
F here in the third state.
No, this is this geometry here. Yeah. So basically, here I'm looking at pi's, probability measures, which are in this half space.
That's true for any
Any f, but the q thetas were defined with respect to f. Yeah. Be really careful. We've got a family of log likelihood ratios to define a parameterized family of probability measures. And so.
f was chosen arbitrarily.
Yeah, well, it's not arbitrarily because we're trying to prove Chernov's theorem. Yeah. We're carefully choosing the likelihood ratio because what we're going to prove is that the empirical distributions, I mean, you'll see it, they just go to q star. On this event, that the averages are much bigger than they should be. A is bigger than the mean. The empirical distributions just go to q star. I'm not going to prove that, but you'll see it. It's just going to be clear. All right. So let me be careful here. So what you do here is that you've got a line here where I'm grading equal to A. And what you end up doing is you draw another band. You take a B which is bigger than A, and so I've got an upper bound. I'm just trying to get a lower bound. So what I do is I bottle up I look at this strip instead of a half space. Okay? So the probability of being that the averages are bigger than or equal to A, remember, that means the empirical distributions are out here. I'll write that down again. So the event that we're interested in, so this is a set of omegas. So the set of omegas such that the sample path average at time n is greater or equal to A. The whole point of empirical distributions is to get this linear interpretation to say that's the same as the empirical distribution at time n dotted with f, as we've described, is in this half space. It's exactly the definitions, okay? And that is a bigger set than being. So one event is being in a half space. Another event is being in this little strip, which is the intersection of HA and HB complement. All right, so we're going to look at that probability instead because we're trying to get a lower bound. I'm going to have to write this down again, but it's okay. Okay, everybody buckled in? Let's do it. You're not buckled? And this is like, I mean, I can't stand holding it, like looking at a teleprompter holding my notes. So I might make a mistake. I'll try to slow down, not do it. But I can't stand holding anything. So I'm just going to do this. So I've got this thing here, which is the expectation of the indicator function. I better expand this out. All right. Oh, Jesus Christ. I think I forgot to tell you something. I explained the likelihood ratio for one random variable. I didn't for a whole sequence of a random vector of length n. We should maybe stop for a second. There's a lemma we need. So if you take any expectation of any function of x1 through xn, here's an example. I'm looking at taking f of xk and taking an average. That's a function of all the guys. I gave you the likelihood ratio of just one random variable. Well, there's a likelihood ratio for them all. This is exactly equal to the expectation of under y but times the likelihood ratio. I feel bad about that. So I should have said that right away. So we defined this for y1. We said this is how, you know, where the yks are distributed according to q theta, you know, and xk is distributed according to p. It's just that you've got the distribution of x1 through xn is just the product of those marginals, you know. And the y is also ID, and the distribution is just the product of the marginals. The probability that y1 is in a set and y2 is in a set is the probability of the probabilities. And for each one of them, the likelihood ratio is e to the L theta yk. So this generalizes. My definition of likelihood ratio generalizes. All right? This is really, really crucial. Okay. You know. All right. So that's true for any function g. Under the caveats, okay, g's measurable, the expectations make sense, so say bounded, you know, this, as long as it's well defined, that's true. Okay, so that's the thing here, is I want to take that as my g and slip in this likelihood ratio, take the expectation with respect to q, but q star, and the reason for that is obvious, because if I take the expectation with respect to q star, I'm looking at something which is typical, you know, I'm looking at the probability that the average is, you know, it's in this little boundary, you know, that happens all the time. The average is going to, you know, going to be in this strip, you know, pretty likely. And I really wish I had put in a lower bound already, but it's okay. Okay, so I've got equality, 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 and I'm just going to leave that as an exercise. I said it was true for one, it's true for sequences as well. But what I want to do is I want to use the fact that L theta is related to F, and this is a star there, sorry. So the thing here is just like a positive number times F minus a constant, And here I'm putting a constraint on that thing, all right? Now, I'm going to get a lower bound here by making this more constrained. And by making this more constrained, I can use that to bound this guy, all right? And so what I'm going to do is just put a greater than b here.